Hello friends, today we derive equation of bending stress. That equation is m by I is equal to f by y is equal to E by R, where m that is the moment of resistance, I that is the moment of inertia, f that is the bending stress, y that is the distance from neutral axis, capital E that is the modulus of elasticity, and R that is the radius of curvature. So first question is, what is the meaning of pure bending stress? Pure bending stress, that means when a beam of length is subjected to a constant amount of bending moment. So here, what is the relation between bending moment and shear force? That is the dm by dx is equal to minus f. So here, bending moment that is constant, and we know that constant derivative that is 0. So here bending moment is constant, so this derivative is 0. That means shear force is 0. So when a beam length is subjected to a constant amount of bending moment and a 0 shear force, the stresses set up across the section of the beam due to bending, that is known as a pure bending stress. So here first we discuss about sagging moment and hogging moment. So here first we draw one neutral axis. Neutral axis, that means there is a no stress of any kind. That means there is no compressive stress or tensile stress at this axis. If you give sagging bending moment, stresses above neutral axis are compressive and stresses below neutral axis are tensile. If a section of the beam is subjected to pure sagging bending moment, this type of moment that is called sagging moment. So in sagging moment, stresses above the neutral axis are compressive. Here you can clearly see that when there is a sagging bending moment, stresses above neutral axis are compressive and stresses below neutral axis are tensile. And at neutral axis there is no stress of any kind. This is a sagging moment. So in our case we discuss about sagging moment. And in hogging bending moment, tension zone is above neutral layer and compressive zone below neutral layer. So in our case we consider here pure sagging bending moment. So here we gave moment like this. So this is a pure sagging bending moment. So stresses above neutral axis are compressive and stresses below neutral axis are tensile. Here there is a one diagram before bending and this diagram is after bending. So here we consider sagging bending moment. So we already discussed that in sagging bending moment, stresses above neutral axis are compressive and stresses below neutral axis are tensile. So here that is on neutral axis. So stresses above neutral axis, that is compressive. So here there is a decrease in length, and stresses below neutral axis, that is tensile. Before deriving equation of bending stress, here we write some assumptions in simple theory of bending. First assumptions, that is the material of beam is homogeneous and isotropic. So what is the meaning of homogeneous? Homogeneous means the constituent material is same everywhere. And what is the meaning of isotropic? Isotropic, that means at every point all the properties like modulus of elasticity, Poisson ratios, etc. are same in all direction. Second assumptions, that is the modulus of elasticity is same in compression and tension. So here in our theory we write modulus of elasticity, that is capital E. For compression and tension, that value is same. Third assumptions, that is the beam is initially straight and has a uniform cross section. So here beam is initially straight and has uniform cross section. Next assumptions, that is the beam section is symmetrical about the plane of bending. And last one is the section under consideration is under pure bending. Means when a beam of length is subjected to a constant amount of bending moment and shear force is 0. So the stresses set up across the cross section of the beam due to bending is known as a pure bending stress. So here we assume that the section under consideration is under pure bending. Now we derive this equation step by step. Here, first we consider a simply supported beam subjected to a bending moment m. For example, dx, that is the small length of the beam. Due to bending of the beam, the top layer AC suffer compression. As we already discussed that here we apply sagging bending moment. So top layer AC suffer compression and reduce to A dash C dash, because in compression there is a reduce in length. So here AC suffer compression and reduce to A dash C dash. As we proceed towards the lower layer of the beam, they also suffer compression but to a lesser degree until we reach this neutral axis, because at neutral axis there is no change in its length. As we further proceed towards the lower layer, we find that layers have suffered tension. We already discussed that in sagging moment, stresses below neutral axis are tensile. So as we further proceed, we find the layers have suffered tension and the layer BD has suffered maximum tension and stress to B dash D dash. So this is the condition of before bending and this is the condition of after bending. So before bending, the length is AC, that is compressed and reduced to A dash C dash. Neutral axis, that is RS, there is no change in its length. So RS is equal to R dash S dash. And before bending there is a BD and after bending there is a B dash D dash, and these part are in tensile condition, so increase in length. Here first we consider a layer PQ at a distance y from this neutral axis. So after bending, layer PQ is compressed to P dash Q dash, because this is the above neutral axis and we already seen that above neutral axis there is a compression. So after bending, layer PQ is compressed to P dash Q dash. So there is a compression, so there is a decrease in length of PQ layer. So before bending, for example, length is 10 centimeter and after bending length is 8 centimeter. So change in length, that is 10 minus 8. So here we can write change in length, that is PQ minus P dash Q dash. So decrease in length of PQ layer, that is delta L is equal to PQ minus P dash Q dash. PQ, that is original length, so change in length, that is PQ minus P dash Q dash, and we know that strain is equal to delta L by L. So strain is equal to change in length, that is PQ minus P dash Q dash, and original length, that is PQ. So we get our first equation, strain is equal to PQ minus P dash Q dash divided by PQ, equation number 1. Here from figure we can clearly see that O P dash Q dash and O R dash S dash are similar. So here we write two sections O P dash Q dash and O R dash S dash that are similar. So are similar. So here by CPCT ratios are always equal. So we can write that P dash Q dash divided by R dash S dash is equal to, what is the distance of O to P dash Q dash, that is R minus Y, because this is a radius of curvature and distance of this strip from neutral axis, that is Y. So distance of P dash Q dash from O, that is R minus Y, and distance of R dash S dash from O, that is capital R. So here we can write P dash Q dash by R dash S dash, that is distance of O from P dash Q dash, that is R minus Y, divided by distance of R dash S dash from O, that is R. So here we multiply minus sign both side. So minus P dash Q dash divided by R dash S dash is equal to minus R minus Y divided by R. Then we add plus 1 both side. So here plus 1, here plus 1. Now take LCM. So here R dash S dash, that is LCM. So here we can write R dash S dash minus P dash Q dash is equal to, here R, that is LCM. So here we can write capital R minus y. So here R dash S dash minus P dash Q dash divided by R dash S dash is equal to R minus plus Y divided by R. So R cancel out. Here, instead of R dash S dash, we can write RS. Why? Because R dash S dash, that is the neutral axis, and we already seen that at neutral axis there is no change in length. So R dash S dash, that is equal to RS, and RS is equal to PQ. So here we can write R dash S dash is equal to RS, because R dash S dash, that is neutral axis, and there is no change in length in neutral axis. So R dash S dash is equal to RS, and from figure we can write RS is equal to PQ. So R dash S dash is equal to RS is equal to PQ. Put this value in above equation, so we get, instead of R dash S dash, we can write PQ. So PQ minus P dash Q dash divided by, again R dash S dash, that is PQ, so divided by PQ is equal to Y by R. That is equation number 2. So from equation number 1 and 2, it is clear that strain is equal to Y by R. So from equation number 1 and 2, from equation number 1 and 2, it is clear that strain is equal to Y by R. So what is the value of strain? Strain, that is the bending stress divided by modulus of elasticity, because we already know that modulus of elasticity, that is the stress by strain. So strain is equal to F divided by capital E, where F, that is the bending stress, capital E, that is the modulus of elasticity. So instead of strain we can write F divided by E is equal to Y by R. So rewrite equation as F divided by Y is equal to E divided by R. This is equation number 3. Again I repeat, here O P dash Q dash and O R dash S dash, that are similar. So here ratios are always equal. So P dash Q dash divided by R dash S dash is equal to R minus Y divided by capital R. Then multiply minus sign both side. Then we add 1 both side. Then we take LCM, and here R dash S dash, that is neutral axis, so there is no change in neutral axis. So R dash S dash is equal to RS, and from figure we can write RS is equal to PQ. So here we can write, instead of R dash S dash, that is PQ. So PQ minus P dash Q dash divided by PQ is equal to Y by R. So from equation number 1 and 2, it is clear that strain is equal to Y by R, because here PQ minus P dash Q dash divided by PQ, here PQ minus P dash Q dash divided by PQ. So from equation number 1 and 2, we can write as strain is equal to Y by R. So what is the meaning of modulus of elasticity? That is stress by strain. So strain is equal to stress divided by modulus of elasticity. Here bending stress, that's why we use symbol F. So F by E is equal to Y by R. Rewrite equation as, so F by Y is equal to E by R. That's equation number 3. From equation 3, it is clear that F is equal to Y multiply E by R. So here modulus of elasticity remains constant, radius of curvature remains constant. That's why we can rewrite this equation as F proportional to Y. So bending stress depends on the Y. As we increase distance from neutral axis, then bending stress is also increases, because F is directly proportional to Y. So here it is clearly see that at Y is equal to 0, bending stress is 0, and as we go upward, distance of Y increases, bending stress is also increases. So here at layer AC, bending stress is maximum. Similarly, at BD, bending stress is maximum. Now we draw section of this beam. Here we draw section of this beam and consider layer PQ at a distance y from this neutral axis. This is a very small layer, so area of this PQ layer, for example, that is dA. Now we find force on this layer. So force in this layer, that is stress multiply area. How this equation come? Stress, that is force per unit area. So force is equal to area multiply stress. Here bending stress, so F, and area of this layer, that is dA. So here we can write force in this layer, that is equal to F multiply dA. So from equation 3, we can write as F is equal to Y multiply E by R. So put this value here. So instead of F, we can write Y multiply E by R and area of this layer as it is. So force in this layer, that is Y multiply E by R into dA. Now we take moment of this layer from neutral axis. So moment of this layer from neutral axis. What is the meaning of moment? Moment, that means force multiply perpendicular distance. So here we can find moment of this layer from neutral axis. So force, that is Y multiply E by R into dA, and perpendicular distance from neutral axis, that is Y. So multiply Y. So rewrite this equation as capital E by R into Y multiply Y, that is Y square into dA. So this is a moment of this layer from this neutral axis. So how we can find moment of whole section? That is algebraic summation of all such moments about neutral axis. So moment is equal to algebraic sum of these moments. So sigma E by R multiply Y square dA. But value of modulus of elasticity and radius of curvature, that is constant. So E by R sigma Y square into dA. So in our previous video, we already discussed about moment of inertia. So what is the meaning of moment of inertia? For example, this section area is dA and perpendicular distance is y. So moment of inertia, that is the second moment of area. So first time we take moment, that is y multiply dA, and second time multiply perpendicular distance. So moment of inertia I, that is y square dA. So here put the value of moment of inertia. Instead of y square multiplied dA, we can write as moment of inertia, because moment of inertia, that is the second moment of area. So first time we take moment, that is dA multiply y, and second type moment, that is multiply perpendicular distance, that is y. So moment of inertia is equal to y square dA. So here instead of y square dA, we can write moment of inertia. So m is equal to capital E by R into I. So rewrite this equation as m by I is equal to E by R. That is equation number 4. So our third equation is F by Y is equal to E by R, and here E by R is equal to M by I. So from equation number 3 and 4, we can write as F by Y is equal to E by R is equal to M by I. So from equation number 3 and 4, we can write as M by I is equal to F by Y is equal to E by R. So this is the equation of bending stress. So here, what is the meaning of M? That is moment of resistance. I, that is the moment of inertia. F, that is bending stress. Y, that is the distance from neutral axis. Capital E, that is the modulus of elasticity. And capital R, that is the radius of curvature. In this way, you easily derive equation of bending stress. Again, I repeat this step. Here, we consider layer PQ at a distance Y. There is a small layer, so consider the area, that is dA. First we find force in this layer. So force in this layer, that is stress multiply area. So stress, that is a bending stress, and area of this layer, that is dA. So instead of F, from equation number 3 we can write Y multiply E by R, and area of this layer as it is. Next we find moment of this layer. So what is the meaning of moment? Moment, that means force multiply perpendicular distance. So force we already find, that is Y multiply E by R into dA, and perpendicular distance from neutral axis, that is Y. So perpendicular distance Y. So moment, that is E by R multiply Y square into dA. So here, what is the meaning of moment of inertia? Moment of inertia, that is the second moment of area. So I is equal to y square dA. So instead of y square dA, here we can write moment of inertia I. So m by I is equal to E by R. So from equation number 3 and 4, equation number 3, that is F by Y is equal to E by R, and equation number 4, that is M by I is equal to E by R. So from equation number 3 and 4, we can write as M by I is equal to F by Y is equal to E by R. So what is the meaning of M? M, that is the moment of resistance. I, that is the moment of inertia. F, that is the bending stress. Y, that is the distance from neutral axis. Capital E, that is the modulus of elasticity, and R, that is the radius of curvature. So in this way, we easily derive equation of bending stress. Thank you.